Alright, so we're going to be proving the limit law for the product of two functions using the formal definition. And to start off, we must first define what the two functions are and what the limit of the two functions is going to be. So let's have two functions. So we let f and g be functions that is defined on an interval centered at a, which is a real number. Except maybe not at a. There still may be a limit at a, except a may not be defined. Now, since we assume that f and g is defined, we can write what it means to take the limit of f and g as x approaches to some value a. So we have limit of x approaches a of f of x. Let's say that approaches L. And we have another limit as x approaches a of g of x. And let's say that approaches to some value m. And L and m are all real numbers. Now, what it means for the limit law of two products is that we want to show that the limit of as x approaches a of f of x times g of x is equal to L times m. So now we have this. Let's try to write this formally in terms of epsilon and delta. For all epsilon greater than 0, there exists delta greater than 0 such that as the distance between x and a decreases, this implies that f of x times g of x gets closer and closer to L times m. Okay, so this is what we want to prove. Let's write want to prove. So now that we have this statement, let's try to fool around with it, see what we can get from this part. So let me rewrite this part. F of x times g of x minus L times m. Okay, so if I were to look at this briefly, I would, first of all, I would want something in the end to have something like this. F of x minus L times something maybe, and then another thing, which is g of x minus m. Because if we have this, we know this function is defined, and we know this function is defined, so we can set any value of epsilon, preferably like epsilon over 2 or something, and then it is guaranteed that we will have a delta that satisfies the condition. So looking at this, if the final thing were to look something like this, it wouldn't be good. The reason why is because if we set this to be something epsilon something and this to be epsilon something, we're gonna have epsilon squared, and that is going to be really hard to solve. So preferably we want something that looks like this. We want a constant or another value, preferably that we know, so preferably something in L or M, followed by the function another constant 1 times g of x minus m. This way we can set this as epsilon over 2c and this as epsilon over 2c1, and this will cancel out, this will cancel out, so it'll be epsilon over 2 plus epsilon over 2, which is epsilon, and then we'll have the proof. So we want to manipulate this question, and to do that, we're going to write this plus L times g of x minus L times g of x minus Lm. Notice that these two is 0. So we're adding nothing to the equation. But now if we were to group these two together, so if we group this with this and this with that, we get, and we can factor this. So grouping it, you get g of x times f of x minus L plus L times g of x minus m. And this is exactly what we wanted. We have some constant, maybe we'll have to manipulate g of x into something, into preferably like m or L, so that it's a constant, but we have these two, and we can set epsilon for these. Now, simplifying this more, we can write that is smaller than or equal to f of x minus L plus L, we can take out the L, well, we can take out the x here as well, g of x here, times g of x minus m. And this is because of the triangle inequality. Okay, so now that we have this triangle inequality here, we have to take something, we have to manipulate g of x into something that we like more, preferably L, something in terms of L or something in terms of M. So let me describe that in brown, and we can come over here. So we have the absolute value of g of x. What can we do? Well, let's try what we did before with the plus minus, which equals to 0. Let's try making g of x, and since we know g of x is defined and that limit as x approaches a of g of x is m, let's try plus minus m. So minus m plus m, and immediately we see that this over here is something that is defined, or something that we can achieve with epsilon. And if we were to separate this by the triangle inequality again, you have g of x minus m, which is smaller than or equal to plus m by triangle inequality. Now, we have this, so we want to put something in terms of this, because it still has g of x. So let's look to the function g of x. What the function is that as limit as x approaches a, g of x equals m. It states that for all epsilon greater than 0, there exists a delta, let's name it delta 1, greater than 0, such that as the distance x and a grows smaller, This implies that g of x minus m is smaller than epsilon. And this is true because we assume that g of x is defined on an interval that is centered at a, except maybe not at a. And so we can choose any epsilon, and there it exists by definition a delta that will satisfy the condition. So for simplicity, we can take epsilon equal 1. Why not? Because epsilon has to be greater than 0, so let's just take 1. This means that g of x minus m is smaller than epsilon, which is smaller than 1. And by definition, there exists a delta 1 greater than 0 that satisfies this. Now, if we were to plug this thing back into what we had for g of x, let's take our arrow. This is strictly smaller than 1 plus absolute value of m. Right? Because we have g of m is smaller than 1, which is that. Okay, now that we've confirmed that absolute value of g of x is smaller than 1 plus absolute value of m, let's continue writing this down. We have 1 plus absolute value of m times the absolute value of f of x minus L plus L. And for simplicity, let's try to keep this symmetric, plus 1, because 1 plus absolute value of m and 1 plus absolute value of L. Technically, we can continue having this, but it's just simpler because if you think about it the other way, if you were to add m times f of x, it will be L plus 1 times g of x minus m. Now, we have these two here. And from here, we want to get some epsilon, right? We want to choose an epsilon such that we can state that a delta exists. So if we look here, since f and g are both defined, we can choose any epsilon we want, and there's guaranteed to be a delta that satisfies the condition. So if we were to choose, because we want this to be equal to epsilon over 2, we want this to be smaller than epsilon over 2, which is equal to epsilon, which then we have proven the thing. So we can choose this to be epsilon over 2 times 1 plus m, and this to be epsilon over 2 times 1 plus absolute value of L. And if that were to be true, we can cancel this with that, and we get epsilon over 2 plus epsilon over 2, which is epsilon. Now let's highlight this in green. Whoops. And let's highlight this in purple. And we can go to this side to prove that again. So we want absolute value of f of x minus L to be we want to choose that to be smaller than epsilon over 2 times 1 plus m. Right? Yeah. And since that we know there will be a delta, whoops, there will be a delta 2 greater than 0 such that this is true. And secondly, we want g of x minus m smaller than theta over 2 times 1 plus s of the value of l. And similarly, we know that this will also be true. And to reiterate, we know this is true because f and g are defined on the interval centered at a, except maybe not at a. And so because of that, their limit is defined, and that means for every epsilon value, there will be a delta that satisfies this. So now that we have finished basically the preliminary work to prove this, let's begin with the actual proof. Start by writing proof. We let epsilon be greater than 0. We will let the epsilon be equal to 1 in the definition of of g of x, of the limit, g of x's limit. This means that implying that there exists a delta 1 greater than 0 such that 0 is smaller than x. Delta 1 implies g of x minus m smaller than 1. We take epsilon over 2 times 1 plus L for definition of G. Which implies that there exists a delta 2 such that this is required. Which implies that there is a delta 2 that satisfies this. And third, we will take epsilon over 2 times 1 plus the value of m for the definition of f of x says limit. If I were to write this more rigorously, I would write the limit of f of x approaches some L. This implies there exists a third delta that is different from the other deltas, such that 0 Okay. Now that we have these three, let's take a delta for the actual proof. Take delta equals the minimum of all three deltas. This way, we know that delta is smaller than all of these three, and that each of these statements that we wrote will be true. And since these are true, that means the implied statement also is true. Okay, now that we've proven that, now we have to finish the then part of the actual statements that we want to prove. Then we have f of x times g of x minus lm. Let's simplify away this in our rough sketch. And this is strictly smaller or equal to by the triangle inequality. And now, since we've proven that g of x now we have to prove that g of x is smaller than 1 plus absolute value of m. We can do that over here. This implies that g of x equals g of x plus, let's write minus m. And by epsilon, we know that this is smaller than 1 plus absolute value of m. And now we can sub that in. We know that this is smaller than 1 plus absolute value of m times f of x minus L plus 1 plus absolute value of L, 1 plus absolute value of L times g of x minus m. Okay, and now we know that this is smaller than 1 plus absolute value of m. If we were to sub back in epsilon, smaller than epsilon over 1, 2 times 1 plus absolute value of m plus 1 plus L times epsilon over 2 times 1 plus absolute value of L. Now we were to cross this out, cross that out, cross that out, cross that out. And we get epsilon over 2 plus epsilon over 2. And that concludes the proof. Alright. Thanks, guys.